Madam, shall we resume the session? Madam, are you there, madam? It says murder. Hello, ma'am, are you there? Means murderers. Are you there with murder systems? Are you there, ma'am? I'll stop saying this. Okay. I don't know who's Jyoti. Hello, Jyoti, can you hear me? Maybe. Okay. Okay, we'll resume. Ashutosh is not there, right? Just give her a call and just ask her to join, please. Because if they miss this, then they'll not be able to understand, and the entire day will go for a waste. Just give her a quick call. Yes, please. Okay. I think we have done this wherein we have checked the data type, correct? Yes. So monthly charges is float, understandable. Total charges is float, understandable. Then we had another senior citizen is integer variable, tenure is integer. I think that's good enough for us to proceed, right? Now what we'll be doing is you want to see that, is it? Right. One very important point which I'd like to mention here at this stage is when we are talking about classification problems, and this is a point which you need to keep in mind, right? One of the key problems is most of these problems will have a peculiar disease, and that disease is that there will be a class imbalance issue. She can hear, right? Okay, so there is something called as class imbalance issue. You have to use the exact language here. This is the class imbalance issue that you will encounter. What is this class imbalance issue? See, we have the dependent variable, which is churn. Ideally speaking, why am I building a model? I want to identify the characteristics of a churner, not of a non-churner, because a non-churner is harmless. Churner is harmful, but typically because of class imbalance and such things, the proportion of churners will be very, very, very tiny, and the proportion of non-churners will be massive. Right? If you're talking about COVID infections also, when we are modeling the data, this is a peculiar issue that you'll see that the proportion of churners may be less than 1%. Non-churners will be 99.95%. Now, if you feed this data into any algorithm, the model will do exactly opposite of what you want it to do. What will it do? Because the sample size for non-churners is massive, it will learn and pick up the characteristics of non-churners, not of churners. It is like if there is a child and I am teaching 9 hours, I'm teaching it mathematics. 1 hour I'm teaching it, let's say, science. Correct? 99%. Let me just give you a different set of numbers. 99 percent of my time, my energy is devoted to teaching the child mathematics, and I don't pay any attention to science, what do you think will happen in the exam? She'll naturally do very well in mathematics. When it comes to science, she'll underperform. The model is like a child. Its brain works like a child, wherein if you supply an overdose of non-churnous data and an underdose of churn data, you will achieve exactly opposite of what you wanted. So this is a peculiar problem which is called as class imbalance issue. How to handle class imbalance issue? There is a technique which is called as SMOTE technique, SMOTE. I will not be covering this. This will be taught to you in machine learning and such things. I will just tell you whether to identify whether or not there is a class imbalance issue. You're already familiar with the group by statement. So let me just run a group by statement. Let me quickly run a group by statement. So I'll see here that non-churners are 5,174, churners are 1,869. It looks decent. That is my first impression. So 5174 plus 1869. Let me go ahead and execute. It is around 7,043. I'm interested in the yes category, which is 1869. So let me just divide this by 7,043. Let me go ahead and execute. 26% of the data represents churners, which is decent. If it is not decent, let us you get substandard results at a later stage. You might want to come here, revise this in the sense use SMOTE. There is class imbalance, but it is not a worrisome issue wherein you have 19 over. It is not an overwhelming issue. It is fine. It is. I think the model should still be able to learn something. Negate the results in the sense that you have built a model for healthy people. But many times the problem may not be about healthy people, right? Because let us say in a real time scenario, I built a model, right? Like? It is showing all the yes, yes. Reverse it, change it. Let it go on to build a. Let it carry on and learn the characteristics of a healthy people. So the model should be able to identify whether a person is healthy or not. That's what you're saying. And out of the model, if it says yes, then I will check that we cannot do. Here, the learning itself will be heavily tilted in favor of healthy patients or churners because 74%. Right. So that is one right unhealthy thing. Right. So class imbalance issue at this stage, you have to come back and look at it. At a later stage, if you get a problem. If I can identify like how many churners are there, then remaining will be churners. So if you can identify, see the moment the model, think from the model's perspective, the model is so very well trained to understand the behavior of churners, sorry, non-churners, that even if there is a churner, there is a greater tendency for it to call him as a churner. Because the model has learned the characteristics of, learned the behavior of non-churners. Even if a person is a churner, there is a greater tendency for it to be misclassified as a non-churn, which means that so many people will churn, non-churn is one thing, monetary impact will be there. But in the case of patients, healthy patients, unhealthy patients, if unhealthy people are getting classified as healthy people, then you are depriving them of good, valuable treatment. He may go on to die. Correct? That becomes a serious problem. Yes. Yes. No, ideally speaking, 50-50, right? Ideally speaking, it should be 50-50. You give 50 churners, 50 non-churners, then basically the model learns. Right? That's a good, that's a fair expectation. I'm giving one churn data and 99 non-churners and expect it to learn churners. How is it practically possible? Thumb rules are there. Thumb rules saying that give 10% churners, that this and all. That 10% is just 10%. It's just a thumb rule. It is, exactly. Yes, it is dominating the behavior. Right? It is dominating. There might be some trait of a non-churner. Sorry, of a churner. There might be some quality of a churner. Let's say diabetes. People with diabetes, they have a greater tendency to sort of contract COVID. I don't know. I'm just giving an example. But because of 99% people, out of these 99% people, many diabetics might not be diseased people. So diabetics will not be identified as a differentiating factor at all. It will go undetected. So that is a big problem. So we have 26%, which is decent. Now comes the first problem which we will be tackling. If you remember, our dependent variable was coded as what? No and yes. I hope you recall. No is a word and yes is again a word. Algorithms cannot understand words. For an algorithm, for a machine learning algorithm, it has to be converted to numbers, right? So where we will be converting no and yes to 0 and 1. You can see here, what am I saying? Convert churn from yes, comma no to 0, comma 1, right? How there is something called as label encoder. Label encoder. So pre-processing dot label encoder function, I'm going to save as LE. That LE dot fit I'm going to use on the dependent variable, and I will be transforming this variable. This one, sir. This is just listing, sir. I mean, you can ignore this actually. LED, what are the classes that are present? That's what we are seeing. No and yes. Now what we will do is we will say a DFN. This is DFN. I'm going to create a new variable which is called as DF of Y. Now, when you say DF dot head of, right? There is a new variable here, Y. Can you see this? No has been coded as 0. Every no has been coded as 0, and every yes has been coded as 1. Every yes is coded as 1. What is it? So, sir, have you run this command, sir? In the beginning, from sklearn import pre-processing. Have you executed it? The first code. Done. The first is LE equals pre-processing. Here, basically, you are calling LE dot fit your fit it. Good. Yes. No to 0, yes to 1. Yes, we can inverse transform your tools. Within this LE itself, inverse transform. So there is something called as inverse underscore transform, wherein zeros will be converted to 1, 1 will become 0. Okay, so for the first problem has been handled, which is of dependent variable. Now we have independent variables, correct? So one portion is done wherein I've taken care of the dependent variable. By and large, dependent variable looks good. Now we have to focus our attention on the independent variables. Independent variables, we had some of these variables were numeric, others were string. That string, we have to now find a way to convert this into your numeric. Okay, so let's later drop this. So you can see here, now we have 21 variables, one additional variable y, which is being read as integer, which is a good sign. There are no problems at all. Now let us display the columns in this particular data set. So df.columns. So this will spit out all the columns here. df.columns. It's an attribute, it's not a function. Correct? df.columns, it's an attribute. Data type of this is an object. Now here is the thing. If you visualize this, all the categorical variables I have to separate out and the numeric variables I have to separate out. So let us begin with this. Let us separate out the categorical, independent categorical variables. Right? Let us separate out independent categorical variables for conversion into numerical. How do I separate this out? So here you can see I am labeling this as x underscore categorical. You can see here, this is a wonderful function, df.loc. df.loc is a very useful function for subsetting the data. You can see here, colon, comma, here, all the variables like gender, partner, dependents, phone service, multiple lines, so on and so forth. All of them I am fetching and right, I'm creating a separate object called as x underscore category. Concatenating all that, extracting. Yes, yes, yes. I'm assembling basically in the data set. I'm collecting, in other words. How do you get this? Because yes. So basically, you can just copy paste the same thing and delete whatever is not wanted. Right. So customer ID anyway is gone. Gender, senior citizen, we've already seen most of them, except for all our category. And you can also do that by just for the logic. The object now. That's what the all the objects. Yes. Sorry. So far it's clear. Sorry, all the string data I'm separating out. If you see here, this list, in this list, can you see this? X underscore categorical, monthly charges I'm removed, total charges I've dropped, right? Which other variable? Payment, monthly charges, total charges. Tenure variable I'm dropping, senior citizen I'm dropping, 4 variables. Why? Because all the numeric variables I'm dropping, only the character variables I'm taking as an object. So now let us just examine the top 5 rows in this particular data set. Do you see one single numeric variable here? Can you see here? X underscore categorical has only, categorical data, right? So we are separating categorical and numeric information.
So in this section we have used what log just for different which separate the
Yes, log is a simple way, right? Log x dot log helps me subset the data set.
I'm saying we can directly do it. Just
That also correct.
That's what I'm saying. Like, is there
No, there's no. Yeah, you're right. You can do it like that. Just subset the data set. Correct. No, I don't see any reason like that. Now let us display the shape of this. There are 15 columns which are. Yes. Now what I'll do is I will separate out all the numeric variables. Correct? Earlier, all the categorical variables went. Now only the numeric variables I'm collecting. Long in the regression also. Yes. Okay, so far we are clear. Separating out numerical and categorical variables. Okay. 15. Let us just check the head. Let's just use the head function, right? So yes, we are right. Almost all of them are numeric. Next is basically the step wherein we will be using dummy coding. Convert categorical variables into dummy coding. How? PD dot get underscore dummies. This is the function that we will be using. Get underscore dummies. PD dot get underscore dummies. And I'm passing that all the categorical variables, right?
Increase to 10.
Yeah. X underscore num1, I'm saying. Let me go ahead and execute this. Now the X underscore num1, you can see how is it creating the dummies, correct? Female and male. The code is written in such a way that it is creating two, it does not have brain, but we have to pick and choose maybe one. This will go. For each variable, it is creating so many variables. There may be additional variables. We don't need so many things, correct? Because this is redundant information, right? So anyway, it is just creating dummies, which I can use, which I can go ahead and use. So 41 columns it is generating, 5 rows it is generating. Now let me just concatenate all the numeric columns. So these numbers, now that these string data has become numeric, can I not concatenate with these 4 variables? Right, so that I have a set of only numeric data. So this is what I have. So pd.concatenate you do to come up with your final X. Final X pd.concatenate. So far we are clear. Now, how does my final X look like? So to understand this, X dot head of, you can just see here, right? All the variables have now been converted to numbers. So this is how you have to have any data before modeling. In machine learning, you can't have string data and such things, right? Isolate. What did I do? Isolated all the categorical variables. Use pd.getDummies, very simple function you can remember. And once you do that, all of these string data or categorical data will become numbers. Now you can use this to build a logistic regression model. We'll do that. We'll do that. So far it's clear. So far it's clear. Dropping will do. We just do. Right. Now create a dependent variable. I think I have already created it. If not, we can just. Yeah, I think earlier it was caps Y. Now I'm just making it a small y. You can ignore this. That's okay. Okay. Till here, we have prepared our base data. So far, what have we done? Have prepared our base data. Right? Now we are ready to go ahead and build our model. Right? Now it's the same thing. Same old story. Now we are ready to build this model on converted data, he says. Right? Let me use train test function. Train underscore test underscore split. I'm just specifying. Log range anywhere. Yeah, but I think you can keep it as DF itself, otherwise you'll get confused. DF of Y. Yes, the X and the Y, that's it. Yes, concatenated. Yes. Corresponding Y. Y is there separately, right? Y we have already created somewhere here. I'll just show you.
Y as a data frame. A column.
Yeah, let it be a column, no problem. Create dependent variable df of y equals y. Now I can use this directly. You can see a 0, 0, 0, 1, 0. This is sufficient for me. df of y. Remember, it's like a seed wherein we can pick up the same records. Here 75% will be used for training. 25% I'm assigning to test data set. Yes. Yes, 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 yes. Model diagnostics will be slightly different. Yes, it can sit, not a problem. No. In fact, if you want to specify it here, let us say if you are concerned that it is separately sitting on, you can just say df of y. It will access it from the data set. Yeah, yeah. So far, we are clear with this code, everybody. Murugesh? Amin is. Okay, so I'm just creating this data set. Okay. Let us examine the shape here. Correct. Let us check the shape of y here. What do I have? I have 5,282 records in the training data set. For y also, I should have 5,282. If this does not match, the model will return errors. If you have not done the missing value step properly, this will show error. This will show a mismatch. Sorry. Right? Even if there's one record which is missing, it will start crying. What? I'm not able to understand what you're saying. One column. It is not returning that. Ideally speaking, what you're saying is right. Right at the beginning, if you see here, from sklearn.model selection, import train underscore test underscore. Sorry? One function, model selection. Yes, 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 yes. That's more than enough. We need to call it no, no, it's fine. Let's just check this for the test. Sorry. Okay, so far it is clear. These usually at this stage, if you have done everything correct, these numbers should match. And if the numbers are matching, it's a good sign the model will not. Sorry, the model will work. The model will work. Okay. Otherwise, if there is even the slightest mismatch, then the model will not work. Okay. Now our usual game plan, wherein we will be instantiating the logistic regression model. Correct? Logistic regression model is what we will be instantiating. Okay, we've just called this function. Now let us go ahead and check one more thing, whether there are missing cases in in training data set. Ideally speaking, if you have done everything right, it should be 0. In the training data set, I'm checking whether there are any null values. See, by and large at this stage, when I say prepare our base data, we are reasonably sure that by and large, the base data is like the foundation that is ready. So if this does not give us good results, we have to play around with the model. We don't want to come back to model, rebuild the entire model. It will necessarily become a big mess. Let us fix up some things at least, right? Some ground realities. Right, XYZ things we are not going to change. I don't want to change the data again and again, because then there'll be, it's like a Pandora's box. Once you open up the data, you're questioning the data itself 100 times. You will just, right? Now at this stage, basically at line number 45, what we have is line number 45. I would say 43. I would say train we have created, test we have created. It is clean. By and large, we should not be unnecessarily questioning the data. By and large. Right? If none of the models work also, I may come back, revisit this. That's a different matter, but that should be a last resort. So once you have prepared the base data, which means that your foundation is ready, on this foundation, you can construct any multi-story building. But in the foundation itself, again and again, we are hammering down the foundation, bringing down the house, bring down the house, but don't bring down the foundation by and large. So what I'm saying is, okay, so we are good to go here. Now let us go ahead and fit this particular model. We will be fitting the logistic regression model. Sorry? He's funny, right? He's right now TCS, Sunrise. So he's been a trainer with Race. He handles fast track analytics and systems. He's also pursuing his PhD with Shinu Madam and JBS. So he's a good person in case you have any, he's especially the capstone, when you're doing your capstone assessments, you run into any challenges, problems, always a good person. Right? Even otherwise, after I leave, after this module is over, if you have any concerns, if you have any if you need any problems to be resolved, if you want any books, if you want certain concepts to be revised, good person to keep in touch with. He's almost 15 years he's been working in the industry now, right? 12 years.
And like, say, I'm here from BA01. From past 5 years, I'm associated with Race. So the reason for asking him to introduce, because I'm from past 2 years, I'm working from home only. So everything happens online. So no much interaction with the participants. So if you need any help, or mostly I would be taking care of your mock interviews and your capstones and all. I would be mentoring a couple of people for capstones. At the same time, I would be handling a couple of modules, not all. So if you need any help as such, with respect to any of these particular mentor sessions, so you can reach me anytime. And my number is already added in the group if I'm not wrong. If not, we will ensure that. You can call me whenever you need any help. Thank you so much.
You want to sit? No.
Thank you.
Thanks a lot. So far we are good. So we have fitted the model now. Okay. Now, see this log. Is not there. Anybody getting error? Sir? No, I'll tell you. Okay. So the problem is turn it off for some time. Yeah. So where are we? In this missing value, sir. That's where you've got it. You might have overlooked one step. I'll tell you, sir, after running this, after running line number 15, please go back and impute it with me. Yeah, first time it will give an error. Now that you're coursing it will become numeric. Now it will not give an error. So and all the other codes also you should again run after this. Okay.
Number 15 should come first and then finish.
Yeah, you can see this. You can see that. Yeah. Your first coercing it, then your imputation will be. Right, coefficients, we've been able to get it. Right, coefficients, right? So as before, we are just getting a set of numbers. We can't make head or tail of these things. Now, what we need to do is basically put a label to this. How do we sort of put a label to this and make it more meaningful? Correct? It looks like a lot of things. There's nothing here. I'm just trying to label it. PD.data frame, x.columns. I'm converting this into a data frame. PD.data frame, transpose this coefficient. Otherwise, you'll get it like this row wise. I'm transposing it. And because I'm using concatenate function, I have to specify this argument value as x axis equals 1 because I'm looking for a row by row concatenation. What is it doing? This is not a mirror. Click on the circuit. This usually one of the arguments. So this is a Python documentation for logistic regression. Dual false tolerance, C is equal to 1.0 fit intercept. Maximum iterations. Can you see this, sir? Yeah. So this instead of 100, just give it to 500. Because what it is saying is that 100 iterations it has reached. It is not able to go beyond that. Because there is a cap on the number of iterations. So just try to increase it to 200 or 300. So far we are clear, guys. So COEFF. So this is your coefficient for logistic regression. Right. So here, wherever you see negative, it means that it has a negative effect on churn. Females have a negative impact or negative effect on churn because when the gender is churn, sorry, when the gender is female, they are less likely to churn. For males also we're getting a negative number. So whichever variables have a negative number, just have some water. Okay. Just see this. Right here, how did we interpret the coefficients in the case of linear regression? 1 unit increase in independent variable, what is the corresponding impact? The impact is by and large same here everywhere. But when you look at logistic regression, here it has a separate impact. Separate impact, separate impact. Here the impact is bigger. And here again at the right at the initial point and at the tails, the impact is different. It's almost not getting up at all, right? It's almost parallel to the x-axis. Here you see almost like a slope and the impact is more. So we can't interpret the coefficients of logistic regression the way we interpret the coefficients of linear regression. It is not like I increase 1 unit of this, the corresponding impact will be that. So the coefficients basically, they either increase or decrease the impact of churn. That's what I can say. Not to what extent, I'm a bit hesitant to comment on it. Because at different places, it has different impact. So far it's clear, right? Okay. Now looks like the positive impact is because of total charges and monthly charges. Because these are monthly charges, total charges, and senior citizen, including payment method when it is electronic check. These are variables which tend to have a higher propensity to churn. I hope this makes sense. Especially this is coming out well because if the total charges increase, propensity to churn increase, which means it's becoming expensive. Therefore, the person is leaving. Monthly charges increase. Therefore, the person is as it becomes expensive, a person is likely to churn. So these coefficients you have to think of, correct? Whether it is making business sense. Here, imagine that we had a negative value. Then there's something suspicious or something, a point which you're missing. How is it that monthly charges are increasing and propensity to churn is coming down? That is counterintuitive. Is this variable good or bad? That's what you have to start thinking. Correct? So when will people, the business will trust when you have less counterintuitive results and something which is more straightforward, right? Something is becoming more expensive, I'll leave. My propensity to leave will increase. Yes. Okay. So coefficients are clear. Now let's move on to another very interesting and a slightly, if I can say, slightly debatable area, which is generating the model diagnostics here. How do we generate the model diagnostics here? There are quite a few diagnostics here. I'll just try my best to impress upon you some of the important diagnostics. Huh? No, the T would not have come. So we just. Yeah, sure, sure. Will you take long time or? No. Okay. Sure, sure. I'll just wait for him because if he misses this out, then again it'll be a problem. Okay, so quality of the model is what we're talking about. So first is basically we can generate this log dot predict. This is my logistic regression model. I'm using the predict function where on the test data set. Correct? Are you able to understand? So I will be capturing the prediction as a variable name called as classes. Clear? So if you sort of click on classes, what is it giving you? 0, 0, 0. This is the predicted class. Are you able to get this? Log.predict will give you the predicted class. But out of curiosity, let us say you can also generate the scores here, which is called as log.proba. Log.proba test underscore x attribute error log.proba. Okay, so when some commands do not work, the best is basically logistic regression. Let's go to the documentation. Let us see what attribute does it have. A predict underscore proba. This is what I wanted to. This is what I had to use. Predict underscore proba function. Predict underscore proba of x. So let us just try this. Correct. Are you able to understand something out of this? Very are you able to get this scores? See, there is a 93% chance that the first fellow will be a non-churner, and there's only a 6% chance that he will be a churner. 93 is greater than 6. Therefore, it has put him as a non-churner, 0. Second individual, see, 82% chance that he's a non-churner, only 17% chance that he's a churner. 82 is greater than 70, so he will be called as a non-churner. Third fellow is again a non-churner, 64 and 36. So decimals will be there, right? So to add up the decimals also. So 93.7 plus 6.2, if you add, roughly it will add up to 100%. It has to add up to 100%. So this is very, very useful. You know, what is this property called? This is a property which is called as interpretability of the model. Because these are statistical models, they are interpretable, right? It's like the model is telling me, boss, why have I called the first 3 individuals as non-churners? Because there's a greater propensity. Now, if you're looking at a lot of other machine learning models and AI models, they are what is called as black box approaches. Machine learning, when you learn They will be able to tell you that it will just be showing you the classes, but you will not tell you how to interpret the model. That's a big tragedy there. Right? Here I'm able to interpret it better. Okay. So print classes. I'm applying the model on the test data. Amit. When you look at the size, it is 1761. Classes dot size, it is 1761. So far clear? Now let me grab the shape of the positive cases in test data. In the positive, right, there are 434 cases who are churners, where in the data. There are 434 cases who are churners. I'm just grabbing the shape of the data. This is what we had already in the data. Yes, we already have. We'll see how whether the model is predicted this. Not even prediction. See, if you look at the this thing command here, see, this is printing positive cases in the test data, comma, test underscore y. I'm subsetting. I'm counting the number of ones in the test data. I'm counting the number of churners in the data. Now we are going to see whether our model also. Yes. This. Yes. Correct. Print the number of negative cases in the data set. So far it's clear.
Your speaking is like bias.
Why bias? Yes, because yeah, see, if the godown itself is faulty, the showroom will also reflect the fault, right? The main data set itself, there was class imbalance that is also reflected in test also. Okay. Now comes some of the metrics that we have to look at. The actual metrics are, right? We have built the model, we have applied the model, but what we have not done so far is basically tested the model. Now, to test the model, what we will be doing is we will be looking at what is called as confusion metrics. We will be looking at what is called as confusion metrics. Print of confusion metrics, right? Metrics dot confusion underscore metrics. This metrics I've already called in the first line of command. To what you You're going to show the code? Shall I share the code? Okay. Are you able to understand what we are doing here? Partial squares. Real is good. Partial squares. So far it's clear, everybody? Are you getting this? Right? Everybody is getting this? Correct? Now, what I'll do is basically I'll open up an Excel sheet to sort of clarify certain points here. Right? So this becomes very important for you. There are two things. One is basically the actual data. Second one is the predicted data. So here I'll be calling the actual on churner. Again, here what you have is insert the predicted category. My prediction. What I have here is basically churn versus non-churn. Are we clear with this? This is my prediction. Okay, can you help me fill these numbers? These cells. What is it? See, be careful here. Here it is prediction, correct? It is in the bottom. We have to just imagine at the this thing front. Okay, 0 is basically non-churners, correct? So, so this is a problem. So this has to be non-churners. So here again, I have to sort of change this to non-churners and then basically churn, right? So look at this non-churn and non-churn. Can you tell me the number 0 versus 0? Predicted is 0, actual is 0. How much is it? 1189. Now predicted is 1, actual is 1. How much? What is this? Predicted is 1, actual is 1. 2, 4, 1. You're right. Correct. Now actual is churner, but predicted as non-churner. Where is it? Actually he's a churner. Predicted as non-churner, 193, correct? Actually, he's a churner. So predicted as non-churner. How much is this? 193. And this is 138. Okay. So this is my predicted category. This is my actual category. And these are the. So this is basically what is called as confusion matrix. What you're seeing in front of you is basically used as a measure to check the quality of the model. Here you will not get R square. There you got one single metric R square in the case of linear. Here you will not get this. Here we are comparing the actual and the predicted category, correct? Let us say if the actual and the predicted match, it means that the model has correctly predicted. If the actual and the predicted do not match, then we are in a problem, right? So let's just take a look at this. Actually, he's a non-churner, but the model, actually he's a non-churner. Model also is saying that he's a churner. So let me just color this with blue because this is the correct classification, right? you're actually a churner. My model is also saying you're a churner. Now look at the second, this thing. Actually, you're a churner. My model is also saying you're a churner. It's a good thing. So here 1189 cases are what? A person is a non-churner. The model has identified him as a churner, with a good side. This is basically a person is a churner and the model also has predicted him as a churner. 241 such cases are there, which is again a correct number. Are we clear? So in a confusion matrix, the diagonal elements represent the correct classification and the off diagonal elements represent the incorrect classification. So if you look at the white cells here, white colored cells or the non-colored, uncolored cells, whatever, they are basically your misclassified cases. Are we clear with this? Now, there are certain labels that you need to keep in mind, certain ideas. So when a person is a churner and the model also has predicted him as a churner, this is called as true positive. The adjective true here means that the model is giving you the right direction, right? The model is doing a good job. The model is basically giving you the correct hint there. How many such true positives are there? 241 cases. Is it clear? Now, this is negative. What is true negative here? A person is a non-churner. My model also has classified him as a non-churner. So how many such cases are there? 1189 such cases are there, which you can call as true negative. The adjective true means the model is correctly identifying non-churners as non-churners. Are these two labels clear? Because this is very, very important that you understand this. Okay. In logistic regression, right? Why are we using logistic regression? That point should be very clear. That sigmoid curve should be very, very clear. Correct. Then class imbalance issue you should highlight. Then these are the model classification. Then we have what is called as false positive. Right. What are we calling as a positive category? See, I'll just put this in bracket. For me, a churner is a positive characteristic. A non-churner is basically a negative character. So I'm just going to put a negative sign here in the bracket. Are you clear with this? Right? When you say false positive, he is not a positive person. He is not a churner. But my model has falsely called him as a churner. Which number should I use here? Predicted as churn. So this is 138. The model is falsely indicating him as a churner. So next is basically you have false negative. He is not a non-churner, but my model is falsely calling him as a non-churner. Right? How many such people are there? 1/9. Are these numbers clear to you? In the interview and such things, please highlight these things, right? I built a model, I got a high accuracy, right? That is not the way you, right? That is not the correct, right, thing that you have to highlight here. Then you also have our good old statistic here, which is the sample size, which is nothing but a sum of all these things. In Excel, basically, it is returning a sum as 1761. 1961. Are you clear with this? True positive, true negative, false positive, false negative. Now, to calculate the overall accuracy of a logistic regression model or any classification model that you learn henceforth, not just in my class, even in anybody else's class, what you can do is you can derive a metric which is called as overall accuracy. What is this overall accuracy business? Put a equal to sign here. Correct? Take the sum of the correct classification or simply TP plus FP. Yeah, my apologies. TP plus TN, you're right. Right? Correct. So just take the sum of these two things and then divide this by the overall sample size of 1761. You're ready here. The overall accuracy of our logistic regression model is 81%. Is this clear? What is TP? What is FP? What is TN? What is FL? How do you derive the overall accuracy of the model? This is a simple way in which you can sort of arrive at the overall accuracy of the model. Now, TP? Yes. Why TP by TN? TP plus TN divided by overall sample size. Okay. Now, when we grew up, basically, we used to stop here for a long time, 10, 15 years when we did statistics, overall accuracy was it. But actually, these days, they look at other metrics as well, because this is not a comprehensive metric. Accuracy is good, overall accuracy, right? Can I just give you a situation, just a scenario, right, of 10 cases? Imagine that you have ID. I'm just cooking up a scenario so that you understand. All right? Person is a churner, second person is a non-churner. I'm just randomly typing some things. How many such cases are there, boss? 6, is it? 7. Change the number slightly. Let me make this as 1 and 1. This as 0. This as 0. This 0, 0, 0, 0. All right. When I count this, what am I getting? I'm getting a count of 1. Correct? So this is not ID. This is the actual class. Are you able to get this? So let us say the model predictions, right? Right, the model has predicted, correct? What has the model done? Model prediction 0, 0, 0, it has predicted, right? Now here, if I look at the cases, what do you see here? Is this a correct classification? Do you agree? This is a correct classification. This is also correct classification. One is classified as 0, one is classified as 0. That's a misclassification. This is also correct classification. Correct. Now, if you were to take the overall accuracy of this case, how much will it be? 8 times it has got right out of 10 instances. Am I right? Am I right? So this is a highly accurate model. Are you able to get this? Highly accurate model, but is it a usable model? All right, that accuracy is basically it is like a shield, right? We say it's a mask behind which there are a lot of interesting details which are hidden. So a highly accurate model, but it is not a usable model because it is not doing a good job. Why is it? Its accuracy is based on the fact that all the zeros have been classified properly. It has not been able to classify one single churner as a churner. So it's not a very usable model. Correct? Now let me just tell you another situation. What is this other situation, boss? Right? Let us say you are dealing with a non-statistician, right? You're a data scientist now. Then tomorrow you're talking to a non-data scientist. Now, when you're talking to a non-data scientist, he does not understand what's a model. Why do you need logistic regression model? Why do you need this neural network? Access things. He says, boss, you have the data. No problem. I will classify every. Okay, this is his prediction. I don't know. This is, what should I say? Mr. Suman, some guy here, okay, some person. What he does is basically he calls everybody as a churner. He blindly, no need of model, no need of your any machine learning model. He calls everybody as a model. He has still got it right. What do you think so? Actual versus correct? Then right? This is a random guess. There is no mathematical formula and such things. It's just a random guess. You give any record, I'll put it as 1, 1, 1. I'm still right most of the times. So what is the use of building a model? Even without a model, I'm able to capture so many cases, right? You give me any case, I'll call it, churn. Why do I need a mathematical model, statistical model, sigmoid curve, that curve, Python, Jupyter notebook?
But sir, the scenario is different. Here we can say channel, but the patient is diabetic and non-diabetic. In this case,
Yes. So again, these two are extreme cases which are very, very dangerous. So this is where, see, this is a good model. This may also be accurate, but it is not a precise model. Precision is different. Precision in the sense, it has got it wrong, correct? 0 is predicted as 1. It is imprecise. First case is imprecise. Second case is it's imprecise. Third case, it is precise, 1 versus 1. Fourth case, it is precise. Remaining 6 case also, it is imprecise. So here, the model lacks precision. So over and above, the point that I'm trying to make here is basically over and above accuracy, there are 3 other metrics that you need to look at or at least quote. What are these 3 metrics? One is what is called as precision. Second one is what is called as recall. And the third one is what is called as F1 score. Precision, recall, and F1 score over and above your accuracy. Are we good with this? Are we good? So let me just show you the formula. Precision is a lot easier. See, this is the formula. Precision equals true positives divided by actual results, or TP divided by TP plus F. This is a simple formula for precision, right? So if I have to evaluate how precise my model is, precision, right? What will I do? Is just a case of TP divided by TP plus FP. This is what I need to do. How will I do this? So where is my TP? TP is nothing but 241, which will be part of the numerator. Put a division symbol, open parenthesis, TP plus FP, which is 241. Then again add it up with FP. Which is 63% is the precision of the model. The model is precise. Here, when we say TP, right? True positives. Right? Are you able to understand this? Are you able to get this? The best way to remember is the first letter of P is precision, and here in the right side, each and everything will end with P. Best way and a simple way to remember this. But here, what am I doing here? See, this is the distinguishing factor, FP. This is the factor, right? False positives I'm putting in the denominator. You know why? many times, if I want to punish a model for or penalize a model for having excessively false positives, excessive false positives. Excessive false positive means unnecessarily it is putting everybody as 1, 1, 1, 1, 1, 1. Right? This will go into the denominator. Correct? As the denominator becomes larger and larger, overall quantity becomes larger and the precision will come down because denominator increases, overall quantity comes down. The opposite is also true. If this guy becomes closer to 0, it's a good sign because then the model precision will go up. So I want my false positives to actually be less. So there are certain scenarios, business scenarios, wherein we want the false positives to be really closer to 0. The false positive means what? Let's just take into consideration a manufacturing sector, right? In a manufacturing sector, I'm just giving an example. Let's say I'm making mobile phones, correct? A lot inspector comes and he picks up a random sample of mobile phones and is checking whether this mobile phone is defective or not defective. Now, for every small scratch or for every small little problem, or because the person has not been trained, though it is a good mobile, the person says that it is a bad mobile. Right? So what will you do? You will take it, perhaps you'll throw it in the dustbin or you will not use it, whatever, right? You may not use it. Correct? So here, false positives become very, very important because even if there are 10 good mobile sets which do not see the light of the day, it means basically that you will be taking a hit because it's a good mobile phone, but it will not reach the customer's hands. So false positives I take very, very seriously under some circumstances. Therefore, here in these cases, false positives, I want to penalize a person for being excessively pointing out good cases as, wrong cases as positive cases. Correct? So this is where your precision becomes important. There's another metric which is called as the recall metric. This is called as the recall metric. This is precision. The second one is what is called as recall. So the numerator does not change here. TP divided by TP plus FN. Here, this is TP plus FN. Look at the formula here. TP divided by TP plus FN. So only this quantity, that is FN, is the only quantity which is basically changed. False negative. Right? This is very, very important because here, let's just calculate the recall metric. It's the same thing. We have a TP divided by, it is TP plus FN. How do I calculate this? Just put a equal to, where is TP? This is 241. Let me divide this by, it's the summation of TP plus FN. Where is this FN? 193. So it is 55%. Okay, the last metric is what is called as F1 score. Now this is what is called as F1 score. So what is this guy F1 score here? F1 score is basically derived from precision and recall. So take 2 here, right? It's almost like the harmonic mean, right? Between precision and recall. 2 times precision into recall divided by precision plus recall. It's a derived metric. So here your F1 will be equal to 2, which is multiplied by precision times your recall This entire thing will be in the numerator. Put a division symbol. Then what you want is precision plus recall. In the denominator, you're taking the sum. So your F1 score will turn out to be roughly around 60%. This is the first model that I've built, right? When do I choose a champion model? Let us say tomorrow I build a SVM model or a neural network model. How do I decide whether that model is better? So this becomes your baseline model. If that model outperforms this metric, you'll choose that as a champion. Is this clear? Precision, recall, and yes. They don't add up to 100%. They don't add up to 100%. They don't add up to 100%, right? So under what circumstances do you use precision, and under what circumstances do you use recall, right? So just take a look at this, please. All right, let's just finish this. See, when there's a high cost associated with false negative, right? Those situations wherein there's a high cost associated with false negative. Which are those cases? Let us say you're doing fraud detection, correct? For instance, in fraud detection or sick patient detection, if a fraudulent transaction, which is actually he's a fraud, is predicted as non-fraudulent, correct? Predicted negative, the consequence can be very bad for the bank. So in fraud detection and such things, this is a recall is something which you should emphasize. Similarly, in sick patient detection, if a sick patient goes through the test and predicted as not sick, the cost associated with false negative will be extremely high. If the sickness is contagious, like COVID or any of these things, he will not be treated at all. So this is the thing with your recall. Now, what about precision? Precision. Now, this, please read this, right? Is a good measure to determine whether the cost of false positive is high. For instance, email spam detection. In email spam detection, a false positive means that an email is non-spam and it has been identified as a spam. It is not a spam, but it is predicted as a spam. The emailer might lose valuable or important information, important emails, if the precision is not high for the spam detection. Is this clear as to how we identify, do the model diagnostic? This has got nothing to do with R square at all.
According to this model, they got the precision as 64%. This says this is the precision of our model. In the future classes, can we optimize this to reach to those?
Oh, definitely. Definitely it's possible. That's why we built it. This is one model. if you use a different model, maybe the precision will increase. We can have a model which is more precise than what we have. Maybe if you use a neural network or SVC, we can just test it out of curiosity. We can just test it. Will we break for coffee?
So it means we have to use another model, not like we use another feature to increase
You can use another model or another feature. Anything you can do. That's all. You're the boss here. You do what you want. But the goal should be that it should be a precise model. If it's not that under all circumstances precision is important, only when the cost associated with the false positive is high, then worry about your precision. Not under all circumstances I want the model to be precise. Low. False indications, false flag should be low.
Actually, we were treating outliers and trying to improve the performance in the earlier classes.
Outliers,
Can
there,
we play with the data here and improve this precision?
save the data.
But that will give any meaningful.
It might, but very rarely. Very rarely. That is not the way to remove, improve precision systems. Here, basically, you have other techniques. You can build multiple techniques. Neural network is one technique. Support vector machine that can be built. And then thirdly, random forest is that can be built. Naive Bayes model is that can be built. Decision tree model is that. You build each of these 5 models, compare the precision obtained by each of these models with the precision. I don't know. It could be that naive Bayes gives you a better precision. So you choose that as a champion. Sometimes what happens is that 5 independent models we build, we can combine 3 models, which is called as ensemble model. Ensemble, which means basically we are stitching the performance of 3 different models. That can be done. So all this is an experimentation process. Nobody can give an answer saying that this model will give you high precision, that model will give you low precision. Try it for your data, whichever works best, you can choose it. So here the emphasis will be more on modeling techniques. There, the case of linear regression, yes, you can change it, but as you said, outliers, deleting one residual cases, sort it by descending order, and whichever has highest residue, remove it, rerun the model. Those are all some of the tricks that we used.
Why I ask this question is, let's say in telecom network, number of call drops is one of the data point, and I will prepare a model and I come to around 64%.
Yes.
Now I have to do something to reduce the call drop. Basically,
Correct.
to
Yes.
increase the precision.
Yes,
So
correct.
what I have to do is what I
Yes.
have to do.
This call drops, if you see here, just do a simple EDA. When the call drops are high, what is the estimated accuracy? What is the estimated precision? And when the call drops are normal, what is the estimated precision? Maybe you want to build 2 different models. One where the call drops are high, second when the call drops are low. Or if the percentage, if you feel that the call drops are very high, there may be 10 or 20 cases. Maybe you want to remove that and then rerun the entire model. When the call drops are normal, what is the precision? That you can just basically, because call drop is such an important factor.
I cannot remove the call drops and see whether something like that should not.
Yeah, ideally not, because that is an important factor. Or it's a simple thing of a cross tabulation. Just do a simple cross tabulation between call drops, high and low. In the column, you can take churn. When the call drops have been very high, what is the proportion of churns? When the call drops have been very low, what is the proportion of churns? You can just tell this. And if you want to include that as a primary factor, then basically instead of linear logistic regression, maybe you can use a decision and then evaluate the accuracy. So that might work better for your system. Put the first column to the first column. One column. It's registered input, right? Correct. ID first. You would agree from all column, from all the variables, or you do manually? No. Then we have to just drop first column equal to in that when we are creating that one. Drop first column equals to yeah. Oh, that's what I'm saying that time. Oh, that's what it's saying. Drop first column, so that if you drop out that column, not for the other. Yeah, because everything is separate columns, right? So n-1 categories is not from first column. Okay, I understand. Okay, got it. Bye. ये थोड़ा I don't know. Somewhere I've moved up. I need your help. So you're seeing, sir? Just okay. You're seeing this? Yeah. I was just I wanted to ask maybe when you're free. Okay, I'm just doing a simple scree plot in PCA. Okay. But I'm just I don't know, made some silly mistake. I'm getting value error again. You've seen scree plot.
The same size. You define where are you defining your x and y? Size.
PD dot plot 1 up to. You can value scatter range one. Is there
X and x name y plus range.
I'll show actually what I want. Okay. Maybe that will help you. It's very simple. I don't know why I'm not able to get it right at all. This is the plot that I want. Scree plot I want. Okay. Y-axis I want eigenvalue. X-axis I've got all the factors, and I'm just trying to replicate this code. Nothing I want. I'm just trying to replicate this code. Only that the data set has changed.
You need find plot get eigenvalue after value you're doing.
Some silly mistake I'm doing. I'm not able to understand what is that silly mistake. This is the data set that he is using.
1 plus 1. What are you doing there?
See, this is the thing that I'm doing.
Oh, you are instead of put shape 1 plus 1.
Where should I put here? Plus 1. Outside?
No, inside.
Here?
Yeah.
Maybe okay.
Down also.
Here?
Yeah.
I think I tried this and eliminated, but anyway. That's fantastic. Thanks. The job is done. I don't know why did I delete it by the way. But what will the shape 1 of 1 do? It will pick up the shape. Add one.
It's just you need to have the same shape of your x and y.
But why should I add one? Shape will just pick up that row, right?
Sure, was scree plot. I haven't tried any.
But anyway, my problem is solved. Thanks. We have to run one by one, maybe. One by one, huh?
I don't know. I need to just read the documentation of that.
Because it will be one extra, right? Yeah. So boss, okay. Okay, come. Come around. You guys are coming?
Not necessarily. It's like you can just, if you want to, you can put it on. Come, we'll have tea. Yeah. I need coffee, otherwise I'll close off. ಅರ್ಧ ಕೊಟ್ಟಿದ್ದೀನಿ.
This you're saying, right? Okay, what data is equal to prefix name, prefix suffix. Drop first equals false, is it?
Yeah.
Or we can give it as true also, right?
We have to give, by default it's false. That's why we give everything.
Okay, so just precision and all are clear. So one suggestion which Mohit was sort of giving is this. What is this? We have generated. So roughly this is what we are getting, correct? 59%, 56% and 59%. Correct? Now, to improve this, Mohit was giving a suggestion. What was the suggestion? He says basically go to get dummies.
There's 36.
Yes. So he says put a comma here. Drop first equals false. So you can just, right? So because we have got for n, this thing we have got n categories. So he says just make this as true. Are able to understand? Right now we are female and male, two categories we have. This will drop first, and then this will help in better precision. That's what he's saying. You can see here it has dropped a lot of variables. From 41 we have reduced it to 26. Correct? Let me just go ahead and run some of these things. This is okay. We have prepared our base data. Okay, this and all are fine. Looks fine. Let me run this logistic regression model. What is the problem? Increase the number of max iteration. Control C. Now control V equals 400. What is this? Oh, yeah. You're right. Well, calling itself I have to give. Oh, yeah.
Yeah, over there we can.
Fit this. Let me get the coefficients. Let me concatenate it. Generate classes. Scores, if you want, you can see print classes, confusion matrix. This is what we are getting. So TP, if you see now, 193 I'm getting.
For me, it's 1
Same, right? Not much of a difference, I think, right?
No, I have given random shade as 50.
That's
what I'm getting.
But-
But for me, precision is like 90%.
90%. For sure.
Yes. I don't know.
Can't be so high. Okay, Shali. Okay, we'll just make a move on, please. Okay, confusion matrix we have seen. Some important things which I wanted to show you, like precision and recall. No need of doing what I have done. This is the first session, so I just wanted to show you right manually. So otherwise, Python itself will give you this precision and recall and such things. Precision, recall, F1. We usually do not look at other metrics like support and such things. So this is the number, right? So 80.9. Just now in Excel, we were able to derive it. We got different metrics like precision and recall and such things. And AUC is also a good value. I'll just tell you what is the AUC. Yes, please.
Again. I don't think it, right? Yeah.
Already have
Okay. It's done, everybody? 80%. Yeah, but how did you get such a big number? Earlier you said. There's something wrong, I feel. Because numbers, it has got nothing to do with random state. It can't take so much. Maybe 4 or 5 cases here and there can go.
See, precision is TP divided by TP plus TM. TP
Which
plus TP.
TP.
Right? That's what I have done. Like manually, it's giving me 90% precision. Manually, 90%.
I think clear so far, right? So this is one way. This AUC is nothing but area under curve. This area under curve is again one more metric which is used to evaluate the model quality. If it is above 0.7 and such things, it's a good thing. Okay. I'll tell you. This chart is called as ROC curve or receiver operating characteristic curve. This is one more way of evaluating whether the model is good or bad. Receiver operating characteristic curve. ROC curve or receiver operating characteristic curve. Just 1 second, please. Okay. See, we have built a model, correct? Right? We have built a model and we have basically understood what is precision. So far we are clear. Where do we use precision? Similarly, we have evaluated what is recall. That part is clear. Now we have evaluated what is the F1 score. Correct. Over and above this, there is one more curve which is called as the ROC curve, which is used to tell how good a classification model is at the end of the day. What it does is we can just finish coding and then we can just resume this. Just type in. this should be X labeled. Okay. 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 See, please understand this. Okay. See, what happens is in your data set of test cases, how many cases you have? Let us say let's assume that we have 1,000 cases for the sake of explanation. Okay. So what this does is you have 1,000 cases, correct? So this is 10%. 10% means first 100 cases. Then 20% of the cases, 30% of the cases, 40, 50, 60, 70, 50, 60, 70, 80, 90, 100. Then you include all the 100% of the cases, correct? You take all the 100%, right? So when you take this, usually there are two scenarios. One is a random model, right? It's like saying, if I take a coin and toss it, a reasonable guess is basically 50% will be head, 50% will be tail, right? So if you randomly take 50% of the cases out of these 10%, right? If you just guess this person will be one person comes. I'm just guessing maybe this fellow is a churner, this fellow is a non-churner, churner, non-churner. By and large, 50% of the times I can still get it right. I don't need any model and such things. So if you are saying, let's say this is 10%, this is 20, this is 30, this is 40, 50, 60, 70, 80, 90, and 100%. If you randomly guess, a reasonable approximation would be that you still should be able to get around 50% right. And if I basically take this as the baseline model, the diagonal line is called as the baseline model. The model accuracy and such things, the test of a model is that it should outperform this baseline model. So this is a baseline model. If your model is also hugging this line, then automatically it means that there is no difference between random guessing and building a model. So the blue line that you are seeing in the ROC curve that we have built should be as far as possible. This is an idealistic situation wherein it is covering the entire area. Usually when you build a model, it may be something like this. It will be like a bow or something, correct? So this area is what we are interested in. Farther this line, better the model. Nearer the line to the diagonal line, the model is very, very bad. So this area, when you calculate, this is what is called as area under the curve. And that in our case has come up to be 0.72. If it is closer to 1, it's a good sign. Max is 1. So that is a simple understanding between area under the curve. So you can just highlight under model diagnostics. Somebody asks you what all you'll be looking at. Capstone projects, how to the two people who had come, correct? So how do we sort of in the capstone project there are certain information that you need to fill, right? What is the expected metrics? Everybody says about model. What about model diagnostics? What all metrics are you looking at? F1 score, precision metric, and recall metric, And these are all some of the metrics that you need to quote, that you need to cite, so that basically it looks like you're a genuine data scientist. That is the ROC curve, AUC curve, precision, recall, accuracy, right? So this completes our entire cycle of learning when it comes to building a classification model. Right. We started off with a logistic regression model, right? Last class we focused on linear regression model. Next one is basically a logistic regression model. 80% of the problems that you see will be mostly a classification related problem. Right? There are multiple classification related problems. One is called as decision tree. That again I have not covered because it will anyway be covered in machine learning. There's also one more called as 9 Bayes, right? Third model, 9 Bayes. And then we have random forest, we have boosting, bagging, all these things will be covered under machine learning. So my goal during the last 4 Saturdays that I got was to sort of give you a thought process about what. First day was all about univariate statistics, proportions, mean, cross tabulation, and such things. We did not touch about statistics. Second day was hypothesis testing, which is the essence of statistics. In machine learning, there you can't do hypothesis testing and such things. Thirdly, the third day we focused on linear model. Logistic regression is also a part of linear class of models. When it comes to more complex patterns, if you are getting low precision and such things, maybe there's a pattern which is not accounted for. And therefore you move on to better models or more complex models, which are called as neural network and such things. Neural network, support vector machine, decision tree, which will be covered in depth as far as machine learning is concerned. Now, what I want to also suggest is that for the paper, for the final examination paper, just please focus on certain important things, right? There can't be a paper wherein we are not talking about ANOVA. ANOVA is a must. ANOVA, analysis of variance is a must. Any paper on statistics will be there in the question. Difference between Pearson's and Spearman's correlation is a must. ANOVA. Pearson's correlation and Spearman's rank correlation. When you do that EDA, pandas profiling, or you can also do it through SciPy, however you want. There are 2 types of correlation. One is called as Pearson's correlation. Second one is Spearman's rank correlation. Pearson's, yes, no. Pearson's correlation and Spearman's rank correlation. Pearson's correlation is a parametric type of correlation. Spearman's rank correlation is a non-parametric type of correlation. Pearson's correlation is used when the sample size is large. Spearman's rank correlation is used when the sample size is low or very small. In Pearson's correlation, basically, you can't have outliers, and both the variables should be normally distributed. Here in Spearman's rank correlation, we don't care whether there are outliers or not. It does not matter. We can still go ahead and do them. These are 2 or 3 parametric. We just highlight that. Normality test, we can just highlight that. Outliers part we highlight. The regression, you just focus particularly what is R square, what is adjusted R square, right? What is the difference between linear and logistic regression model? You should be able to emphasize on that, right? T-test and such things, chi-square and correlation, just understand what's the difference. Okay, how do you check for normality? A simple histogram, you can just check for normality, right? Then 68, 95, 99 property, which we spoke about, right? 25 marks will be for section A, 5 into 5, 25. 5 questions, 5 marks. It will all be theoretical. Next section B will be 25 marks again. It will be a real case study. There will be a case study on which you'll have to go ahead and build the model. So see, usually it will be one model, not two models. It will usually not be multiple. Either linear or logistic. Yeah, yeah. See, one thing which I wanted to sort of show you is this. This lady here, she has done, see, she has been able to build a logistic regression model like this. What she has done is very smartly, she has called that SM package. Do you see this SM? Import stats model, sm.logit. Shall we quickly run this? Just so that we can, right? Anyway, we have built this model. So we'll just round this off by building a what happened? What happened?
No, just the visual.
Madam, are you, I don't know, Shashikala, madam, are you able to follow or not, madam? What happened here? Chat? Yeah, no problem. Right, I think this is a lot easier using statsmodel.api, sm.logit of y comma x. So here again, one interesting thing is that you'll get p-value. You can see a lot of p-values are actually insignificant, correct? Right, a lot of these things actually can be dropped because it is not making much sense at all. Wherever the p-value is greater than 0.05, you can just drop it and rerun the model. Some of them are significant, which you can take seriously. Otherwise, if it is not significant, why bother? All right, this is how we can further clean up the model, because you can see here a lot of these values. Correct. 0.73, correct. Greater than 0.05, insignificant. Drop it and rerun the model. 0.96, greater than 0.05, so drop it and rerun. 0.08, greater than 0.05, insignificant, correct. So the first three variables are gone. It's a good thing. This is, what is this, internet? No, so there must be some problem because it is not able to compute some of the statistics like standard error and such things. Okay, some problems here with okay, one is fine, 0.01, 0.73, again, online backup, you can drop it. Device protection is drop it. 0.03 is fine, it looks good. 0.00 is fine, it looks good.
One also we need to drop, right? Then it says one.
No, one is greater than 0.05, right?
Yeah, so we can drop it.
So yeah, anything greater than 0.05, we should, you're right, sir. Less than 0.05, we keep it, yes. So there are at least 10 variables which you can drop and clean this up. Clean it up further because the final model can be just with respect to 8 or 10 variables. That's it. Huh? Based on this, I'll have to give you one assignment. Right? There is a bank loan prediction problem. Right? You can just try to run one logistic regression problem there.
Data set is present, sir.
No,
You have provided the data set.
no, I will provide it. It is called as bank loan dataset. See, it's a very simple problem wherein this is a separate tool, don't worry about it. So there's a data set here. Can you see here? Age is there, education level is there, employee, address, income, debt to income, credit debt, other debt, and default. You have to predict the number of defaulters, which are the key drivers. And this is a lot simpler because you have got only one categorical variable. Others are all numeric. I think within half an hour you can finish it. Okay. Right. Yes. Okay. So I can give this data set. Okay. So after the exam, next week, I think you can focus on the exam. But after that exam, will you focus on the assignment part? You'll have roughly 15 days. That's what build up, a logistic regression model to identify the profile of defaulters. Yes. Yes, yes, yes. Assignment, any assignment will be evaluated. This one is there, one. Right? Only one, I think you can just. Others, I think you have done some EDA and all, right? If you remember, can you upload that? Will you upload that part? I think you have done quite a bit of EDA and such things, polishing data set, right? Yes, so please upload that. I'll just take it as 10, 10, 10. 10 marks, 10 marks. That is first part of EDA is 10 marks. Whatever this logistic regression, I can consider it for 10 marks. So this assignment, once you upload, basically based on the assignment, I will evaluate you and I'll give you marks. That's what I'm saying. Right? If it is 10, I'll just increase it to 20. I'll just do that. Two assignments. Yes, yes, yes.
And the time period data.
Yes.
Can we get it uploaded in the assignment? The data assignment. That's like how we uploaded for this data set can go there and then.
I mean, can I share this data set with you?
I can. We have to do this next week, right?
Yeah, you have some time. That's okay. Right, you can do EDA and such things and then send it to me. Okay. Okay. So, great. Thank you. Thank you very much. Share it with Amin. I shared the scripts with you, Amin. I shared the scripts with you. Yes.